Okay, this video will focus on the remaining topics not yet covered under periodic motion. So based on the lecture notes, periodic motion covers 7 topics or 7 sections, and the first 4 were already discussed back in the lecture. So we're going to focus on the last 3, which are relating uniform circular motion in SHM, well, simple harmonic motion, the period of a system undergoing such motion, and finally we're going to apply these equations to a simple pendulum in the hopes of getting expressions that we need. For the recap, we have Hooke's law. It's a restorative force. Force of the spring is equal to negative kx, k being the spring constant and x being the displacement from equilibrium. Simple harmonic motion, based on Hooke's law, if Hooke's law or the spring force is the only force present in the system that's non-zero, you have an expression for its acceleration being equal to negative k over mx. And we derive the position function of an object following simple harmonic motion. It can be either x of t or y of t. It's up to you. It's given as a sine square root of k over m times t. X over t is the position, a is the amplitude, k is the spring force, m is the mass, and finally t is the time. So for now, we're starting for relating UCM and SHM. We're relating uniform circular motion to simple harmonic motion because we already know a lot of concepts regarding UCM. And an interesting point is that UCM shares a lot of similarities to periodic motion. If you see on the animation on the right, you have a spring that moves up and down, so it's a vertical spring, and correspondingly on the right side of the animation will be a particle moving around in the circle. What's interesting is the y position of a particle in uniform circular motion, if you graph it as a function with respect to time, is similar to the movement of a spring mass system. We're going to focus later, we're going to see how that works or how those two systems reconcile with each other. So I'd like for you to focus first on the graphic on the left. Here you have a circle of radius a, and you have a particle moving around that circle or moving along the circular path. And it's interesting to note for this system, for simplicity's sake, that we want Vt to be constant, at least the magnitude of Vt. So all in all, we have this circle or we have this particle that moves in UCM. So if velocity is constant, since we're not really considering the radius changing, omega or the angular velocity also has to be constant. From there, we could find the y position as a function of the angle. And this is from your trigonometry lessons. You know that y theta is just equal to a sine theta, a being the hypotenuse and sine theta being the opposite. So that indicates your y values, right? But then from angular kinematics, you know that the angle is related to omega in terms of omega or theta is equal to omega times time. So y may be expressed as a function of time, because as time goes by, your theta changes, and that theta changes according to time as well as angular velocity. So now, instead of y being a function of theta, you now have y as a function of time. You change theta's value on the right side as omega t. And again, I'd like to point out that omega in this instance is just constant. All right? So now, their goal is you have to find an expression for the period t. In periodic motion, period t is the time it takes for any object to return to its original position for its repetitive motion. So we get one cycle of repetitive motion, and the time it takes to complete that is a period t. In this case, the period of a particle moving around in a circle is if it returns to the same angle already, because by then it would have repeated its motion. So we return to the function y of t is equal to a sine omega t. And we have to take note of certain properties of the sine function. You know that the particle is at the same position, wherever the position is, when omega t is equal to 0, as well as when omega t is equal to 2 pi. So you could substitute omega t there with a sine 0 and a sine 2 pi, and you'll end up with the same value or the same location, y location, where the particle is now. So that's also indicated from your trigonometry lessons. Then a cycle is completed when the time is equal to the period. And there's no calculations involved because that's how the period is defined. So we can take that the time it takes for the argument to go from 0 to 2 pi as the period, capital T. So we're just replacing this value of t here as the period, just to indicate it. And from there, we can have an expression for omega. We can have an expression for angular velocity by isolating its value. So it's equal to 2 pi divided by the period. At this point, you know that period is in units of seconds. So your angular velocity is actually somewhat related to frequency, which we will focus on in a bit. Now we're done. We have that expression. So again, I'll just backtrack. We have this expression of omega is equal to 2 pi over t. That's the angular velocity of a particle moving around in a circle in UCM. So now we have to figure out how to get the period of that certain system undergoing simple harmonic motion. And that means not just expressing it in terms of omega, because omega rarely appears in physical systems, in spring mass systems, for example. So it would be useful for us to express period not in terms of omega, but in terms of k, the spring constant, and m, the mass. So far we have two functions of position that undergoes periodic motion. We have the first equation relates to the circle moving in uniform circular motion as yt is equal to a sine omega t. And then the second equation is yt is equal to a sine square root of km over t. That is the equation that we derived from our lectures back then. Please take note that whether you use x of t or y of t, it doesn't really matter. The choice of the variable that we pick is arbitrary. You can have a spring moving along horizontally. You can also have a spring moving along vertically. So from this, we know that both of these equations follow uniform or simple harmonic motion. So we can somehow relate both equations. They can be equal, but then there is a certain condition that this omega has to be equal to something here in the right equation. And simple inspection, we can see that from simple inspection that omega is just equal to square root of k over m. And we have an expression for omega from the previous slide, and we can replace it to 2 pi over period. And now we can relate the period, or the time it takes for spring mass to repeat its motion, that relates to its spring constant, k, and its mass, m. And then if you isolate t, you end up with an expression on the right, on the orange box. T is equal to 2 pi square root of m over k. And it's the period of a spring mass system of mass m and spring constant k. Keep in mind that for this system, the only force present is Hooke's law, the restorative force driven by the spring. We have short comments about the period. Let's try to see how it manifests physically, because right now it's just a bunch of letters for you to, well, hopefully not memorize. So besides the fact that it has an equation that has, well, a mathematical basis, we can also somewhat have, or we can see expected results regarding this equation. So for example, you have heavier masses. You would have heavier objects attached to the spring. It's expected that if you have heavier masses, it would be harder to move the object. So it can manifest as the movement being slower. This means that your period will increase because it takes a longer time for the mass to return back to its original position to repeat its motion. So in math, a higher value of m, it's directly proportional to t. So t is related to the square root of m. And if you look at k, stronger springs, meaning a more powerful spring, kind of drives a stronger spring force for the object, meaning that it drives it faster. Its acceleration is larger. That means its movements are quicker. In this case, if the object moves faster, that means the period will decrease. And mathematically, it should make sense as well because of the fact that k is in the denominator. So that means a larger value of k indicates a smaller value of the period. Okay, so for the simple pendulum, we focus on the free body diagram. And our goal for the free body diagram is to extract an equation like Hooke's law for a simple pendulum. We want to do this because the simple system of a spring mass can give a lot of insight regarding how to determine the period of a simple pendulum, which is what you need for your experiments. So we have a simple diagram here of a pendulum of length L, and that it traces an arc length of S, which we will focus on later, and that the theta that we're going to refer for the next few minutes will be the angle that the string makes with respect to the vertical axis. Then we have the figure for a simple pendulum. Assuming that the system is frictionless elsewhere, there's only two forces acting on the object. That would be tension, keeping the motion of the pendulum alive, as well as the gravitational force exerted on the object of mass m. But then the problem is, so before I show these two, the problem with this is T, the tension, or gravity doesn't really show where, it doesn't show a restorative force. It doesn't point anywhere close to the center. And that's what we want. We want an equation for Hooke's law, and Hooke's law needs the force that drives it back to equilibrium needs to be proportional to its displacement from equilibrium. And that's the focus of S, because S here will indicate how far it is from equilibrium. And the goal is to have a Hooke's law equation that's related to S, and from there, if we do find it, we can find an expression for the period. So now, the easiest way for us to find that kind of force that brings it back to equilibrium, we need to decompose gravity, or the gravitational force. The reason for this being is it's the gravitational force that actually drives the motion towards the center. You notice that at any given point in time, at any given value of theta, our tension will always point radially. So it doesn't really contribute much for the object to move back to the center. If there's a component of force, or if there's a force that we can decompose to find a restorative force, it's gravity. So that would be the force in yellow. And of course, there would be another component that counteracts the tension. So we focus first on centripetal or radial forces, the ones pointing in the center. So we have tension pointing inward. Let's call that the positive direction for our case, as well as mg cosine theta. And if you notice, using geometry, the theta here is just the same theta here when we decompose it. T minus mg cosine theta should be equal to mass times centripetal acceleration. So it's similar to UCM. Well, it's not exactly UCM. It's non-uniform UCM because the speed of the object changes. So you have to take note that the sum of these, or the difference of these two forces, should be equal to, or should drive your centripetal acceleration. You have to take note that centripetal acceleration is still needed, because if it doesn't have that centripetal acceleration, the only present force would be this yellow force, and it will just continue onward away from the circle. So you will need a non-zero acceleration for that. But that's not our focus. Our focus is the restorative force. And the restorative force is given by the sign component of the gravitational force. That's the force in yellow. And if you notice, it will point towards equilibrium. And that if it's on the other end, if you could reflect the image, that arrow will still point toward the middle. So a crucial point here is that mg sine theta is your restorative force. But we have a problem with that. It's not really Hooke's law. Because for Hooke's law, it needs to look like this equation for the spring. That it's, it's proportional to the position. And our x in this case would be s, the arc length. And the equation mg sine theta, there's nowhere in this expression that indicates that there's s somewhere. Again, ft should be proportional to s, because s is the distance from equilibrium. That's the problem. And a lot of physical systems are restricted from calculations because of this problem. So what scientists, or mostly engineers, do is they try to tweak the equation. They try to see that, okay, for small values of the angle, maybe we can work around with something. And the solution for that is, for small values of the angle theta, they figured out that it's actually somewhat very close to the actual value of the angle. So sine theta is approximately equal to theta. Take note that this theta should be in radians for it to make sense, not in degrees. So this changes ft. So if we could substitute sine theta here with just theta, you have an equation for the tangential force, or the restorative force, as negative mg theta. Still no s, but that can be easily solved. Because from kinematics, you know that the arc length is just equal to the radius, and for this case it's L, times the angle. So this could be replaced with negative mg s over L. At this point in time, it already looks a lot like Hooke's law. All we need to do is rearrange some of the values to find this equation. And this equation, if you think about it, this mg over L can already substitute as your spring constant. And this negative sign makes sense because restorative force always has a negative sign because it always brings it back to the original position. And S here is our displacement from equilibrium. From there, you know that there would be a Hooke's law equivalent for the simple pendulums at small theta. And it is very important that you follow this restriction well. That's why we were rather strict in making sure that the angle was never too big. Because as much as possible, supposedly in your experiments, theta shouldn't matter as long as it's not too large. So now we connect the Hooke's law as well as the equation for the simple pendulum for small angles. And from here, we could actually find an expression for the period of a pendulum. So both of them are restorative forces proportional to their displacements from the center, from equilibrium. If you notice, there's no spring constant for the pendulum, seeing it as there's no spring in the pendulum. But then there should be an effective spring constant for it. So instead of writing k, we can write it as k sub p. And if you just compare the two values, x here and s are both in terms of meters. So that means this k should be similar in terms of its quantity, its physical quantity, to mg over L. So the effective spring constant for the pendulum is mg over L. But since we already have an expression for period a while ago that is related to the mass of the pendulum, or the mass of the spring system, as well as its spring constant, we can also have an expression for the period of a pendulum using the same equation a while ago. For that, so remember that the period for the spring, so please take note that this is period, not tension anymore. It's equal to 2 pi square root of m over k. The period of a pendulum then should be 2 pi square root of L over mg times m. So indicate that this is just the reciprocal of k, as in the period of the spring mass system. And there's something interesting about the result because the m's cancel out. So for a simple pendulum at small angles, you have an expression for the period as follows. It's 2 pi square root of L over g. And honestly, at the end of the day, it's just reliant on two things: the length of the string and as well as the gravitational acceleration where you are right now. So you have to watch out for this. Now, while this is somewhat an elegant equation, you have to watch out that there are certain restrictions to it, namely that the angles have to be small. Okay, thank you for listening.